Gambetta.
Okay, thank you for the introduction and good afternoon. And first of all, I would like to thank the organizers for organizing and for inviting me and giving me the opportunity to present our work here and for organizing such a perfect schedule, because now let's say I can continue perfectly previous talk to show you how quantum computers can be used to simulate Fermis, and in particular how can be used to, let's say, gain some insight into the physics of our model. So this work is a joint effort of part of the PHASECRAFT team and part of the Google Quantum AI team, in which we run our software on the Google Quantum device. So I'm currently a researcher at PHASECRAFT, which is a quantum computing software startup. It's been founded in 2019. We currently have 16 people in our permanent staff. And we have 2 offices in Bristol and London in the UK. And our focus is actually to try to get the most out of these MIT quantum computers, with a particular focus on material simulations and simulation of condensed matter models. And as Peter showed you before, let's say the devices we currently have are pretty limited. They are noisy, so they give access only to pretty shallow circuits with a limited number of gates. And we have access to, let's say, around 50 to 1,000 qubits. And last week, IBM just came out with their new devices with 433 qubits, which I think is the biggest machine. Unless it is, okay. At least for now. And we think that these systems are particularly nice for quantum simulations, and that we try to convince you now in this talk. So here is, let's say, some of the recent works we published, and we really try to tackle the, let's say, the many-body problems from different perspectives, ranging from, let's say, designing algorithms for simulation of dynamics, ground state. And also in this recent work, we also try to see which are the costs required to simulate some real materials with these devices. So this is a picture of our team, and in particular, I circled all the people involved in this work. We have Stasia and Jan Lucas, who actually did most of this work, Ashley, Raul, and myself. So I think I don't need to introduce the upper model, but just to set the convention, we set T equal 1, and we measured all the energy units of T. Our aim here is to use a quantum computer to find the ground state and the ground state properties of the Fermi-Hubbard model Hamiltonian. And of course, we know that there are many other approaches which, let's say, so far are superior to quantum computers. We have hexadiagonalizations, which, however, I mean, it's pretty limited in terms of the number of sites that can be solved. Let's say, I think this is the largest distance that has been addressed with hexadiagonalization, even though the work is pretty old. But I'm not aware of any, let's say, more recent work. And of course, we have a plethora of powerful numerical algorithms that we heard this morning and yesterday. And of course, we have analog quantum simulators. So why we should bother with quantum computers? Well, the first point is that I'm not really sure if what we are doing is, say, numerical experiments or real experiments, so it's better to compare quantum computers with both of them. So if we look at numerical methods, a very important point is that quantum computers are quantum. So if we try to describe and simulate a quantum system with a quantum computer, we can implement interactions in a pretty natural way, and we don't need to, let's say, rely on perturbative regimes, so we can actually obtain non-perturbative solutions to, let's say, a quantum many-body problem. We don't have the same problem, and since, let's say, we are using quantum systems, in some way we can exploit the quantum resources in a more efficient way in terms of, let's say, sizes and storage of the many-body wave function. If we compare with analog simulators, one main advantage of quantum computers is that they allow for a full control over parameters and models. So in principle, we can really rely in a simple way any model we would like to simulate, and we can control the parameters with a very high accuracy. We can reach zero-time corrector regime in a pretty natural way. And let's say measurements in quantum computers are as simple as measuring bit strings, even though here there are some caveats, and it's not that easy to make measurements on quantum computer, and we don't have access to all the kind of observables we may, let's say, have access to from numerical methods. So, should we all stop using analog quantum simulators and numerical methods? Of course not, at least not yet. Indeed, current quantum computers are still pretty limited, as I will show you. Let's say the size of the upper model we've been able to simulate are very, very ridiculous in some way. And let's say they allow to measure probabilities and not probability amplitudes. So, for instance, we don't have access to the wave function of the system. And the tricky point is that finding the ground to the general Hamiltonian is QMAR, where QMAR is the quantum version of NP-R problems, meaning that even with the general coherent quantum computers, it may take exponential amount of resources to find the ground state of a quantum system. So the idea here is that quantum computers at the moment may provide a very complementary and orthogonal approach to solve the quantum many-body problems in regimes which are not easily accessible with current methods. So this is why we think they're useful. Let's see, and this device will be useful in the next years. So the first step is to solve take a method matter problem on a quantum computer is to map the fermionic Hamiltonian, which is defined in general as a sum of operators at, let's say, product of a generation operators. And we have to map this fermionic Hamiltonian into qubits, and the original fermionic Hamiltonian into a qubit Hamiltonian, which consists in general of a sum of products of Pauli matrices. One way to do this is via the linear transform, and as Peter told before, this is very simple in one dimension, and let's say the prescription is pretty simple. Open term is just mapped into a sum of products of two Pauli matrices, and let's say that the upward interaction is mapped essentially in the product of the Pauli matrices. But things are a bit more complicated to two-dimension because the Jordan linear transform is essentially a map from, let's say, a one-dimensional system. So if we have, let's say, a two-dimensional system, we first have to, let's say, decide sort of ordering arrangement with which we are mapping our 2D system into a one-dimensional chain. And for instance, you can use a kind of, let's say, sort of this kind of snake ordering similar to the DMRT approach. But the price you have to pay in this case is that the simple open terms can be into, let's say, a pretty heavyweight operators, and in fact, whenever you are trying to implement the interactions between the qubits, which are not neighboring between clients. So more on this here. So for instance, let's say we would like to implement let's say the open interactions between these two modes, let's say to prevent modes to 1 and to 2. And these are mapped, let's say, into qubit 1 and qubit 2 in this Pauli string. This can be done in a pretty simple way, and here we have, let's say, way 2 Pauli operators, so everything is simple. But now if we try to implement interactions between fermionic modes at site 1, and 1, these are mapped in qubits 0 and 3, which of course are nearest neighbors in the original fermionic lattice, but are not neighbors in our Fermi-Hubbard string. And if we try to do this fermionic coping is mapped into a product of 4 Pauli matrices. And the problem is that in order to implement this kind of operation in a quantum computer software, and since we have limited resources, we should try to avoid this kind of situation. One way to do this is to, let's say, implement an F-swap network, which is essentially an operation which swaps the physical state of the qubits. So for instance, now the idea is that we can swap let's say the fermionic, the qubit modes 0 and 1, 3 and 2, 4 and 5, 7 and 6, in such a way that we get this new arrangement, this new journal linear encoding, where now the original interactions between 0 and the qubit 0 and qubit 3 can be implemented in a pretty, let's say, it's just a product of two poly matrices, because now 0 and 3 are neighbors. So I would, let's say, keep in mind this because it will be important for the rest of this talk. The second step is to devise the proper algorithm in this way to get the ground state of the Fermi-Hubbard model. And we use this so-called variational quantum solver, which is a hybrid quantum classical algorithm, which consists of a classical and a quantum part. The quantum part starts with the initialization process, in which the qubit register is initialized in the ground state of a simple Hamiltonian. In this case, is the Fermi-Hubbard Hamiltonian with zero interaction, so that's free fermions. And then we apply what is known as the ANSATZ, which is set of, let's say, a repeated set of gates, and each gate is in principle parameterized by a parameter, which plays the role of variational parameters. And the idea is that after this ANSATZ, you can measure bit strings at the, let's say, at the end of the circuits. You can recombine these bit strings into original observables of the fermionic problem, for instance, the energy, and then use this energy as a cost function in order to, let's say, find a new set of parameters which minimize this cost function.
Is this the same one that whether you do it on a chain or you do it on a ladder?
Yes. I mean,
even though there is kind of difference in locality, stream operators, so you don't know.
I mean, I will show you in the next slide. It's slightly different, but the main idea is the same. So let's say I will explain it in the next slide. So the idea is to repeat this loop many times to find each time better parameters until we reach convergence in the energy. At this point, we know the set of parameters that can be used to realize a good approximation of the ground state of the Fermi-Hubbard model, which is called PQE ground state. And then we can probe this PQE ground state, let's say by same kind of measurements. But the problem here is that we have to take into account the fact that qubits are noisy, and so we need to apply an array of error mitigation and techniques and post-processing in order to clean our data and to obtain something meaningful. Yeah, sorry, it's not in the next slide, but in a couple of slides. So let's say, before showing you our results, I just would like to show you which was the state of the art before our work. And as you can see, the instances that have been addressed were pretty disappointing, let's say around 2 or 4 qubits with limited number of gates. And another problem of this previous work were that they relied on compression techniques, which try to exploit the symmetry of the problem to further reduce the number of qubits required to simulate these systems. These numbers are very, pretty disappointing if you compare them with the resources required to get a highly fidelity approximation of the Fermi-Hubbard, let's say, for instance, the 5x5 instance of the Fermi-Hubbard model. And the part of the PHASECRAFT team demonstrated a couple of years ago that to do this, you need ANSATZ with 300 and 500 layers. And this is, layers, not two-qubit gates. Each layer consists of many two-qubit gates. So this, you have to imagine that you need roughly an order of magnitude more gates to get this kind of accurate approximation. So can we do something with our current devices? Well, yes. And what we showed is that even with simplified low-depth circuits, we can get insight into the physics of the Fermi-Hubbard model. And I will show you that we've been able to see, for instance, the outcome of the metal-insulator transition, detect the electromagnetic order of the ground state, and to see some of the features one would expect for the charges in density. And as you can see here, the sizes of the system we've been able to address were significantly larger than the previous ones. We're talking about 1 times 8, let's say 8 sites Fermi-Hubbard models. But importantly, the number of gates that were applied and the depth of these ANSATZ grew significantly with respect to the previous cases. And importantly, our approach is, doesn't rely on compression techniques. So in principle, once better quantum computers will be available, this can be scaled up in a pretty straightforward way. Okay, this is the core of our ANSATZ, and essentially it is based on, say, what in quantum optics are called bang-bang protocols. Essentially, we prepare the system in the ground state of the simple Hamiltonian, and then we apply a sequence of 10 evolution according to the original Hamiltonian and the final Hamiltonian we want to simulate, or with short time evolutions. So the idea here is in this so-called Hamiltonian variational ANSATZ framework to decompose the original Hamiltonian into sets of non-commuting terms, and each of these sets will consist of terms which commute with each other, and let's say we call a victory layer consists of the application of all these sets in sequence. So for instance, in this 2x4 system, we can identify 4 different sets of non-commuting terms, and we have, let's say, 2 vertical openings, green and blue. We have horizontal openings in red, and we have on-site interactions. So our ANSATZ will consist essentially of this time evolution according to all of these 4 sets, where now, let's say, the duration of these time evolutions represents the variational parameters which is minimized by our approach in the classical optimization. Let's say we actually consider a slightly tweaked version of this Hamiltonian variational ANSATZ, because as you remember, I told you that let's say we need to take care of this Jordan-Wigner problem, and to do that we introduced the Fermionic swap network. But we managed to make things even more efficient by combining essentially the Fermionic swap networks with the horizontal openings. They're acting essentially on the same kind of qubits, so we can just merge them together in a single gate. And this allowed us to, let's say, realize smaller circuits. But the price we have to pay is that now the order in which these terms should be applied is now fixed. So this is another new problem. Okay, this is actually a physical realization of our Fermi-Hubbard model into the Google Rainbow device.
Yeah, can you comment on the advantages of this on-top versus a gap
Well, I think, let's say one main advantage is that, first of all, it's physically inspired. So it's pretty easy to understand which terms are doing what things. Another very important thing of our ANSATZ is that, I don't know if we will have time to show you, but our ANSATZ essentially preserves the symmetry of the upper model. And this will allow us to exploit the symmetries for error mitigation. Another point is that this ANSATZ is pretty compact. We have only 4 parameters per layer. And so this would avoid, let's say, allow us to avoid all the problem of barrel photos or minimization of a large sets of parameters. But of course, and another interesting thing is that it's pretty general. To change systems, you can apply exactly the same principle to get a new ANSATZ. So, probably there are optimized ANSATZ which are more powerful for a very specific task, but then it's not clear how you can extend the ANSATZ to other systems. And okay, yeah, one thing that you can see here is that actually the most native implementation of a 1×8 instance of the Fermi-Hubbard model would have been, let's say, 2 parallel rows of qubits, but actually this kind of geometry didn't fit the device, so we had to resort to this zigzag arrangement. And let's say we went to pay a small price because now, for instance, we want to implement on-site interactions, we need to swap these 2 qubits, for instance, in such a way that now, let's say the spin up and spin down at site 1 are close to each other, and let's say we can therefore implement the on-site interactions. So let's say we can implement this kind of operation with the same Fermionic network I introduced before, but now the principle, the philosophy behind it is slightly different, and it's just due because of the connectivity of the real device, because of course, let's say if we want to implement interactions between qubits, these two qubits must be connected in the real device. While the problem of, let's say, of the other fermionic swap networks and also the journaling the encoding introduced before is due to the encoding of the way in which coordinates are mapped in the qubits and as a very different nature, despite they can be implemented in the same way. So here, for instance, you have you can see the 2x4 ANSATZ, and in particular, this is the paradigmatic step of our efficient Hamiltonian variational ANSATZ, in which we combine the fermionic and the fermionic swap and the horizontal opening in a single step. Okay, finally, let's discuss a bit our results. So here we start by comparing the energies we obtained with in our experiments. Then we are comparing this energy with the exact ground state energies of the Fermi-Hubbard model with simulated energy, meaning that, these are an ideal simulation of our experiment without noise, and what we call later determinant approach, which is just, let's say, the best later determinant in terms of energy minimization that can be find us, that is corresponds to sort of best big field approach one can think about in this case. So the first thing to notice is that our PQE data, which are measured in the real device, are pretty close to the simulated one. And importantly, I forgot to say that these results are for circuit with a single layer. So we apply a single layer of our ANSATZ, and then we measure. We optimize, and then we prepare the ground and we measure. Yes, I think we are using 1,000 shots for the minimization process, and I think 10,000 shots for the actual thinking measurement.
Are you doing that?
Yes.
Oh.
Yes. Yeah, and it is right. The agreement, I think that the very remarkable fact is the agreement between this orange and blue color. And I will show probably, later how we managed to achieve this kind of agreement. And
what's the difference between the simulated and the exact?
yeah, okay. The exact are actually measured in the real device. So let's say we connected via the cloud with the Google device, we perform the measurement and so on, and we can input data that real experimentally. Well, this simulated data are just an ideal simulation of the DQE algorithm without noise that can be done on the computer. In the end, it's just, let's say, we have to apply a set of gates, minimize, and we can do emulating in a classical computer, at least for small instances. So the main difference is that in the simulated, we don't have noise, and in the data, we have the noise of our device. And then, let's say another thing we have to notice is that, we are not doing too badly if we compare to the original ground state of the Fermi-Hubbard model. Of course, it's a single layer ANSATZ, so we cannot achieve the great accuracy, but we're not too far. And importantly, we are doing way better than classical field approach. Okay. So a better way, energies are not probably the best observable to look at, especially because, there may be different phases, so, we're not snapshots. So,
if I change you, because does your calculation get worse for logically because the initial state is an uninterrupted state?
Yes, probably, yeah.
How much worse?
Yeah, probably. You can see already from here that the disagreement grows with larger views, and I will show you, let's say, in a couple of slides, other quantities in which, let's say, this discrepancy is bigger. Let's say, of course, if we increase the number of layers, the problem will be solved in some way, because we know that the DQE, higher that ANSATZ will converge the correct to the correct ground state. But one conjecture is that, we started from the non-interactive ground state, so in some way we expect to do this while we're not able to capture strongly effect of stronger correlations for low density. Okay, so maybe I go very quickly on this. I mean, another better observable to see if we are really preparing good approximation of the ground set is to look at fidelity, which is the overlap between our approximated wave functions and the original one. And we're still, I mean, the fidelity is pretty good, around 90%. But importantly, one thing that you can see is that to increase the depth of the circuit, for instance, I mean, 2 layers of our ANSATZ, the fidelity will improve in a pretty important way, as you can see here, for smaller distance, the 1/4. Okay, but what about some of the striking features of the Fermi-Hubbard model? We were able to see, for instance, the MOTT transition occurring at filling in the presence of the finite interactions in a one-dimensional instance of the Hubbard model. I mean, of course, here you can see that we can see a pretty nice jump of the chemical potential and the function of the rotation number. And also, if you look at the derivative of the chemical potential, we can see pretty nice spike. So, I mean, this is the proof that we're actually seeing some of the correlation effects of the Hubbard model. And yeah, as Eugene was telling before, for stronger U, this, I mean, the agreement between our the EQE ANSATZ, both itself and simulated, and the original ground state here in green is even worse, because I mean, our conjecture is that we need more layers of our ANSATZ to get stronger interaction. But we were able to see antiferromagnetic ordering in both one-dimensional and two-dimensional instances of the Hubbard model. Here, probably the ordering of the two-dimensional is a bit weird, but it's just following the original Jordan-Wigner path. So this is the kind of signal we would expect in the presence of antiferromagnetic ordering, which can be probably seen a bit better if we look at cuts of spin correlation functions along the vertical direction. As you can see here, the disagreement between the ground state, let's say the exact ground state correlation functions and the DQE1 is, let's say, quite big. But we have, importantly, we have, I mean, a good qualitative agreement between the expected behavior of correlation functions and the actual data. The quantitative agreement is not great, and meaning that we really want to get quantitative agreement in deeper ANSATZ. And let's say the same thing if we look at, for instance, charges in densities. For instance, now, I mean, here we have our experimental density, ground charge density, and our exact charge density. And here we're correctly seeing without oscillations due to the open boundaries of our system, but we cannot see Wigner oscillations, which are expected for instance, Q equals 4, and you can probably see low observation numbers, for instance, 2 and 2. Here we have a single peak, and here we have 2 peaks in the exact data. This is again the problem that we need probably with deeper ANSATZ to capture this effect of interactions. And very quickly about error mitigation. I mean, to get this very good agreement between our DQE data and DQE simulation, we need to apply an array of error mitigation techniques. And this can be divided into 2 layers. First, we have a very low-level circuit optimization, in which, for instance, we try to optimize the layout of the circuits by, for instance, alternating single qubit and 2 qubit gates, because this has been shown to be beneficial in terms of error. We selected best qubits, we selected best runs, and we apply speed equal inspired error mitigation technique, which just consists of sandwiching 2 qubit gates with polyxes. And I mean, as you can see here, even this very simple approach allows to reduce the error in a pretty significant way from this upper 4 curves to these lower ones. Then we have techniques. Yeah, I mean, okay. The main idea is that, let's imagine that you have a kind of error in your circuits of this form, so that rotation. The main idea is that if you sandwich this, I mean, if you imagine that at each step this error may occur, and you just insert these 2 polyxes, the overall combined effect is the identity. So in some way, just inserting these 2 x's will correct for any rotation. And since, I mean, you can show that this two qubit gates used and the polyhexes commute, essentially sandwiching this square root gate with polyhexes will not change the result, but it will correct for possible Z rotation occurring, for instance, let's say, either during the gate or just before or after the gate. Selection of the best run. Yeah, for instance, I mean, there is lots of variability in devices, so I mean, each run can be different from each other, just depending on the time of the day you access the device. So once we have the degree parameters, which is not super, I mean, but I mean, it's not a huge variability, but there is a bit of variability. So what we did is, I mean, once we know the degree parameters, we realized 3 degree ground states, and we selected the ones with the lowest energy. Very simple. But I would just want to comment on the very powerful techniques we use, this training fermionic linear optics technique, which essentially is based on the fact that quadratic systems can be simulated in an efficient way classically. So what we can do for any kind of circuits is to create pairs of X of energies and noisy energies measured from a real device. And we can create a map, which in many cases is a very simple linear map. But the idea is that now, since in our Fermi-Hubbard model, many of the terms in the Hamiltonian are quadratic, with the only exception of site interactions, we can apply this map essentially to correct for noisy energies, even let's say behind the regimal validity of this map, just by using this kind of linear regression technique. And the results are pretty striking because here, let's say we start from our raw data in purple, for applied for selection, which are essentially based on the fact that Fermi-Hubbard model conserves the number of spin particles per sector. Our ANSATZ preserves the spin particles per sector as well. And so we can select the runs which conserve this number of particles per sector. And then we apply these fermionic linear optics techniques, and as you can see here, we are showing error essentially. And just by applying fermionic linear optics, we've managed to reduce the error by a factor of 10. And then we applied all of the other techniques, which I hadn't time to discuss, but in the end, without filling, the reduction in the error we obtained is 46x, which is pretty striking, and we'll explain why we managed to achieve such a very nice comparison between exact simulated data and experimental data. So to conclude very briefly, I showed you that, let's say, even with low density answers can help us in gaining some insights into the physics of the Fermi-Hubbard model. I showed you how error mitigation techniques are crucial to do that. And the advantage of our approach is that it can be scaled up in a pretty efficient way, but of course, improvements on the other side are required if you want to access bigger systems, and in particular, if you want to create deeper circuits, which are essential, as I showed you, to capture the effect of strong correlations. And with that, thank you for your attention.
Yeah, the last two points were here in your conclusion. So what are your prospects?
This one?
Both of the last two there.
Well, let's say that the main limitation actually is the gate fidelity. Because I mean, as I told you at the very beginning, now we have machines with 433 qubits, which will allow us to access 200 sites of the upper model with 200 sites, which would be great. The problem is that the fidelity of the gates is not good enough. And this limits essentially the number of gates you can apply. So the prospect on our side, as software company, we can try to improve our error mitigation techniques and to devise more efficient answers. But of course, at some point we need improvements on hardware. But these improvements are coming at a very fast pace, because just in a couple of years we've been able to simulate now in upper models with 8 sites, so with better fidelities. So we hope that in the next 5 to 10 years, we will be able to probably not be classical approaches, but at least to get very close to them. And I mean, a good point is that, of course, now there is a lot of interest in fault tolerant quantum computation, and all the kind of improvements that are made, will be made in that sector are also beneficial for these devices. So I mean, we are all going into the same direction.
Is error built up the reason you don't repeat the inflation in your algorithm?
Yeah, essentially, yes. I mean, you have to imagine that, yes, if you have noisy gates, then if you apply a sequence of gates, the more gates you apply, the more the error will spread. And so this will, in some way, will limit the quality of the signal you can observe. Good point of error mitigation techniques is that if we manage to improve our techniques, in principle, we will be able to tolerate more errors. So even with quantum computers with the same fidelity, but with better error mitigation techniques, we will be able to run longer systems and at the very end to mitigate these errors. But yeah, essentially, the limiting factor on the depth is gate fidelities.
In this, your offhand comment saying maybe 5 to 10 years. Is it just offhand, or you have a sense that what extrapolate from the previous improvement hardware?
No, it's, let's say, it's a hope. We have to ask.
It's just a hope. You're going to compare, let's say, with TMRG with the 106, and that's still 5, 10 years type of thing. That's the state of
To
the art.
catch up with DMRG,
Yeah.
no, we can go 2-dimensional after.
Right.
But 1D, we are hopeless compared to DMRG.
Right. With all the focus on it, still reduction things.
Yeah, the error rates are far more bigger than.
So, but I mean, the idea is that at some point, I mean, of course, for instance, now there was a pretty recent paper in which they managed to address a 48-site system with a very interesting trick of just splitting the system. I mean, just exploiting 8 qubits. I mean, the distances of 8 qubits and averaging over many of these, let's say, kind of replicas of the same system. And this allows them to reach system size up to 48 in a non-perturbative way. So, I mean, of course, we need hardware improvements, but the number of algorithms which are known for quantum computing is very limited. And so, let's say, there is still hope that cleverer algorithms will give us access to bigger sizes. So, I mean, it's difficult, but there are many ways in which kind of improvement can be done. So I think there is quite a bit of optimism.
You draw answers with this time algorithm, right? Still rational answers. So do you know whether it stays expressed enough for larger systems? And you also said that you did not find that it wasn't corrupt, so you did not have many false minimums. Is this also something that you think will persist to larger systems like this?
This is a very nice question, and let's say it's difficult to tell because we don't have access to, I mean, even simulation. That's not easy because, I mean, for instance, I showed you that the fidelity plot we simulated a 2x4 system with layer 2 answers. And I mean, it's not difficult, but it's starting to get challenging. So, I mean, we want to reach 10 layers of these answers. It's not easy to do classical. So it's, yeah, it's a very, of course, it's a very crucial question. If this answer is still expressive, I think we don't know yet.
So what you observe is predominantly the noisy energy, and then you just say that the exact answer is this?
Yes, in practice, yes. I mean, here you have, I mean, essentially you select, or each of these plots will correspond to some parameters of our ANSATZ. And these parameters, say, you can just simulate exactly let's say, which is the energy of let's say, the minimum energy of the decrease, or I mean, the energy of the decrease of this parameter. And then you can measure the same, let's say, your device for the same parameters, and you can construct this map.
So that's the one that comes out from
That's a very good question. In principle, yes. Because essentially, I mean, you have to be careful because you have to spread out these points in a pretty nice way if you want to get a meaningful fit. So in principle, if you change observables, you have to repeat all of this procedure again. But actually, we use this technique also for other observables, for actually all the observables I showed you, charge density and so on, using exactly the same data. So, I mean, because when you measure the energy in the quantum computers, you're not actually measuring the energy, but you're measuring strings of Foley operators. And for instance, the occupation number of each site. And luckily, these observables can be employed to get different observables. So once you have these two sets of, let's say, Foley quantities, you can use them to create different, let's say, different observables. But of course, if you do that, you have to be careful in how all of these points are spread. Because, for instance, if all of these points were just, say, sort of collapsed in a small region, your fit would be meaningless. But yeah, actually, we just use the optimization on the energy, which works reasonably well for also all the other observables.
Okay, so let's thank Filippo again. All the three speakers, listen all. Let's take a break. We will be back at 4:15.
I want to.
Well, let's see. With the current algorithm, with the known ones, we for I mean, this way, now with the cost of some of the, I mean, we use the super record that might be not the best one, but let's say, I think with this framework, probably the very state of the art can be done with the numbers.
We have very little.
Yeah, the current one.
You also need this
So,
that this
I mean, for the lead and improvement on the hardware, but because I mean, the main problem is that
this slow rate.
yeah, we're thinking not here another way. I mean, we're trying to use the example. Not the most
Very strong for we eventually
Think about having some kind of time independent on just take the array.
yeah.
I think it's just.
But so this one
It seems to be a bit small because in the end, we're actually one of the few companies which is focusing on the devices. Because all of the many companies are focusing on so I mean, yeah, but there are not many people actually